We'll now cover calibration. This will be specifically about humidity, but we will cover a few general calibration topics as well. The first thing is, why calibrate? Well, in general, if something's worth measuring, it's probably worth measuring correctly. And to ensure that you're measuring correctly, calibration is a requirement because all measuring devices do drift. Although RH measurement devices, as we've already seen, tend to drift more than most because they are in direct contact with the environment and any contaminants. A question I often hear is, NIST traceable, is that all I need? And the answer is no. Let's use an example. In this case, we have a lock and a master key. Well, that master key can open up that lock, no problem. Very reliable. Now, if we were to take a copy from that master, we'd probably find that the lock still opens. But if we continue to make copies of copies of copies, at some point we would probably find that one of those copies no longer opens that lock. And that's because we've had degradation all along the chain of copies. Now, that copy is still traceable to the master key, but it is no longer able to open the lock because of the degradation. This is very much how NIST traceable works. NIST traceable means there is an unbroken chain of comparisons between the instrument and NIST or some other standards body. It does not mean anything about the length of the chain or how many steps there have been in that chain of traceability, nor does it state anything or mean anything about the accuracy of the instrument. It is very possible to have a thermometer that is plus or minus 3 degrees, yet still be completely NIST traceable. Each link of that chain must be analyzed for degradation to truly understand what sort of measurement uncertainty or accuracy we're able to provide. I'll quickly cover something called test uncertainty ratio. This is a whole topic unto itself, but I think there's a key point that's worth mentioning. And that is the reference device, when performing a calibration, should be significantly more accurate than the equipment being calibrated. And that should be the case over the entire calibration range. Calibrating a sensor, let's say a humidity sensor, with a 2% reference device will not yield a 2% calibration on the device being calibrated. And one must also account for drift of the reference device, which will degrade the overall calibration that much more. So it's important to have a reference device significantly greater than the device being calibrated. 3 or 4 to 1 are typical, although that is difficult to achieve in relative humidity. So we use something called guard banding to compensate for that. Again, that's a topic to itself, but it's important to note that we just cannot simply transfer that accuracy or measurement uncertainty from one device to the other. There's degradation at each step. Well, as we've seen, temperature is critical in any humidity measurement and calibration. A small temperature gradient can cause a very large RH error. At 25 C and 50% RH, just a 0.1 C gradient can have a corresponding 0.3% RH gradient or error if it's a calibration. And at 40 degrees C and 75% RH, a quarter degree temperature gradient will result in a 1% RH error. Accurate RH measurement usually requires an associated accurate temperature measurement as well. Accurate air-based calibrations have unique problems because air has very little thermal mass and is a poor temperature conductor. As a result, when we try to achieve good calibrations in air, we get temperature gradients that must be compensated for. Again, these can certainly be done, but it requires specialized setups in order to achieve it. RH sensors also have an associated temperature response. By that I mean an output from an RH sensor or measurement device at 25 C can be substantially different at 15 C or 40 C even though the relative humidity values may be the same. On this graph, we can see on the green line a device that is operating at 25 degrees C. When that same device is now being operated at 40 C or 15 C, we can see a substantially different output value. In this graph, we're looking at a typical response of a humidity measurement system over a wide operating range of both temperature and relative humidity. As you can see, it is certainly not a flat plane, but quite a curve to it. So it is important to compensate for both temperature and relative humidity if we're operating a measurement device over a wide range. It's important to calibrate any device over its entire operating range. This is particularly true when relative humidity is involved. An RH sensor that is calibrated at 25 degrees C may have quite a different characteristic when operated at 40 C. In fact, it may even be out of tolerance. So it's important that if a device is going to operate at, let's say, 40 degrees C and 75% RH, that it actually be calibrated at those ranges. It's also important to have a full wide range calibration because not doing so may mask sensor contamination issues. It's important to understand that in humidity calibration, it's the surrounding environment that is the reference for the device that's being calibrated. Unlike a voltmeter, for example, where there's a direct connection to a device, in this case, it's the environment that must be measured in order to know what the true and accurate calibration environment is. Uncertainty of the reference device as well as the calibration environment, typically a chamber, must be taken into account, and they can both be significant error contributors. If we look at temperature gradients within a chamber, we can find very significant ones, particularly in the corners and along the walls, and particularly if the chamber is being operated away from ambient conditions. For example, if we're performing a calibration in a chamber at 40 degrees C, yet room temperature is 20 or 25 degrees C, we'll typically find that those corners and near the walls of the chamber will be potentially quite different from 40 C, and those will introduce significant humidity gradients or errors if we're performing a calibration.